the record button just for the sake of it. So we're recording now, even though we've got listen again, but listen again, I checked it 3 days ago and it said it hadn't been uploaded yet. So I'll do a separate recording and put that onto the site myself. So we're into the resources page. Remember, we have to go to the Horizon virtual server. So you know where we are, the C721 page, and we want that link there, which takes us to the Horizon server, the CSEE server that has all the expensive software on. We log in, we go to the Windows link on there, we wait for it to load our profile. It's slow, it must be cold. Okay, we're in. So let's open Multisim. So go down here. Again, I've still got a broken mouse. I haven't managed to get one ordered in yet, so I have to scroll slowly. Right, so Multisim 14.2. Yeah, we're all familiar with that. So we should go to that automatically in the future. So people shouldn't ask me, how do I run Multisim? Okay, but I'll still go through the motions here for you. Okay, we had some problems with the server last week, but really all that was going on there is a switch was broken. This was at the university level, so they soon mended that, which was good. I'm told that I can just roll a mouse in to make this bigger, but it would appear that I cannot. So I'm just going to try something different. This is just so that you can see it more than anything else. So I seem to recall we went up to 250 last time, and that was much better, wasn't it? People could see that a bit better. Okay, so a couple of minutes to get you into the simulator. Make sure you can do that. Out of the way. So without Mike Walton in, it's going to be a bit difficult for me to do the demos and be able to deal with the chat at the same time. So you'll have to bear with me on that. Dr. Walton. Oops, shouldn't share screen with that on, but never mind. Isn't and hasn't appeared on Listen Again till this moment. Yeah. I'm still confused as to whether it's there or not. So perhaps you could update me on that. I don't have any control over Listen Again. That's a central thing. But what I've done for this session is I pressed the record up there. But I think most of what we did last week was introductory, wasn't it, to do with the assignment and so on and so forth, and nothing too exciting really. Well, it's exciting, but nothing too amazingly relevant to your assignment. So even if you picked up at this point in time, I think you'd be fine. Okay, we're still steady at 22, 23. I assume everyone has now been able to open Multisim. And here's my Multisim. Can maximize that. Okay, and I think that's pretty easy to see that. So if you recall, This is what it's all about. We're teaching you to use a piece of software before you start to do your own designs. And if you recall, when we wanted to place components, we simply went to place component, and we could put things onto the screen. Now, I ran a video for you last week, which was about potential dividers, and that was under resources. Let's just go to the web page again. This is how I go in. It might not be the best way of going in. Nevertheless, it works. See the problems I'm having with my mouse, can't you? So into 721, module resources, and down the bottom here is a series of links. And what you've got there is potential divider part 1 and potential divider part 2. So what I'm going to do is I'm going to first redraw that circuit of the potential divider, and we're going to start with a battery on there, and then after we've put a battery on there, we're going to put an AC signal source, because as I say in those videos, and I would recommend that you watch these, they're also on YouTube under Wood-O Woods. I can just put a note if you want on the chat. So many things open here. So inside here on YouTube, simply Wood-O Woods, and go to my playlists, and there are tons and tons and tons of videos from last year. Obviously, we'll be developing videos as we go through this, but I know there's people that like to look ahead, and I've been taking lots of questions during the week about how people can get ahead on their assignment and so on. Well, the answer is have a look at last year. Okay, so just so go to YouTube, type in Wood-O Woods, that's my TV channel, and then just go to playlists and you'll find lots and lots of stuff on there. Still no mic. I'm worried he's not going to come in, but never mind, I'll run it. So let's do some drawing, shall we? Let's do some circuit design. Everyone ready to go on that? Just check the Oh, hello, Mike.
You right?
Yeah. Might need a bit more volume. You're a bit.
Right? Is that better?
Yeah, you're just a bit away from your microphone. That's all.
Yeah, unfortunately, I had everything was working this morning apart from Essex.
Essex?
Yeah. Problem I had, I couldn't log on.
Oh.
Wouldn't let me have it. It was like, nah. How
strange. How strange. I think that VMware was a little bit slow this morning, but I think everyone's in there now. Really, all I've done is just explain. We took a question on Q&As about what the two sessions are. Well, the two sessions are intended to be pretty much identical, but if you watched both of them, you would say they're not identical. Well, the content is, but the dialogue is just for our own sanity. So I'm just going to shut my mail down. You don't want to read. Well, perhaps you do want to read my mail, but I'm not going to let you. So yeah, the essence of the two sessions will be the same, but obviously, as Mike and I sit here and chat with each other, we're not going to have exactly the same conversation. So your screen is not shared. Yep. Okay, but that's because I'm not doing anything at the moment. So we'll just stay in here for the time being. So what we're going to do is we're going to draw a potential divider on the screen. It's just going to be done with resistors, and we're going to put a DC source in there. We're going to connect up an oscilloscope for the first time with a DC source and see what happens when we do that. And then we're going to move on to an AC source with the potential divider, with 2 resistors on it. Okay. So recording's on. I'll upload the recording later because, well, I personally am not happy that Listen Again from last week isn't on there. It should be. When I go on there, it says we'll upload shortly. Mike, can you just do a check for me on 721 webpage? Listen Again. That should be under the first tab somewhere. You don't necessarily need to download, but there's just a hyperlink in there that should take you to that resource. And there's one on there transcribed and there's one on there static. Just have a look for me, would you, and just see if that's there. Okay, so sharing screen. So here we are inside Multisim. Let's get down and do something, shall we? So the first thing that we want to do for our potential divider, just like we did before, and as I say, it's convenient to go over things more than once, because once we've held your hand for a few hours, we would expect to be in a position where you'd be able to do this kind of stuff for yourself. So place component, and remember, in here, we've got lots and lots of different categories. This is all groups at the moment, but we want to go into basic. And down here, look, we can find a resistor. Click on the resistor. Lots of different values. I said to you before, you can just select a particular value, or what you can do is you can just choose any one and modify it afterwards. I prefer the choose any one and modify afterwards method, probably because I'm lazy. Okay, so let's bring that in there, and there is my first resistor. Now I could close that and recall that what I can do is I can right click on it and I can rotate it, translate it, flip it, do whatever I want. But I'm reasonably happy with that one there. I don't mind him there. So now I'm going to place another one. So place components, resistor again, it's already highlighted. I'm going to click OK, and here comes my next resistor. Now I've got to do, I want to rotate this resistor, so I'm just going to plonk it there for the time being. I don't want any more components for the moment, so I hit close. I'm going to click on the component. I'm going to rotate 90 degrees clockwise. Click on the component with the left mouse and plonk it down somewhere there. Okay, 2 minutes for everyone to do that. Now you did this last week, should have done this last week, and hopefully that won't provide any major hiccups for you, okay? So just 2 minutes to do that. Mike, did that run okay, or is it there?
They are, I mean, it's there. It's put itself up as Tuesday the 19th of January's recording, but the event took place in Zoom, and we're currently waiting for the recording to become available. Is the message under?
Yeah, that's what I saw when I went there. The point I made this morning was, Mike, that this is standalone anyway, so really all we did is spoke about introduction, what it is, what we want to achieve. But most of that's documented on the website anyway. This is really where we get into the core material. So even if there is anything missing there, I don't think we need to worry about it too much. Just goes to show you cannot rely on centralized resources, can you? I mean, this is, so I'm just recording this and I'm going to put the hyperlink on it. God knows how. So it's a 3-hour session. Can you imagine how big that file must be, Mike?
Yeah, it's not going to be. It's not going to be small. Yeah, is it just an audio recording, or are they actually recording the video?
They're recording a video. Can you imagine how astronomically large that must be? I mean, a 5-minute one when I upload my YouTube videos are sort of 2-3 gigabytes.
I know. You know, we do like to use 4K to contemplate our looks.
Well, yeah, stunning. Okay, Mike, can you keep an eye on the chat for me and just tell me whether anyone has got any major issues as I go through this? Because I need to keep this maximized with my screen shared, otherwise people can't see what I'm doing. So there's a very strong argument actually to have 2 screens here, but I don't have 2 screens at home, unfortunately. Okay, so no majors yet. I think everyone has managed to do that. Now remember, if I go to the end of the component and I click on it, and I've got a wire coming off it, if I hit the escape button, it disappears. Okay, so go to the end of the component, put it onto the end of the other component, and click on it, and you'll see the wire's gone red. That means it's connected between those two components. Yeah, fine. We're happy with that. Now I think we need to place another couple of components, and one of those components is a DC source, which we're going to basically put a battery in. So I go to components, and back components, and I don't like the look of this mic. I've got a spinning wheel. Place component. Just a little hiccup. We get little hiccups. So I'm going to come back to here. So sources. Well, fairly obviously, a battery's a source, right? Source means where something came from. So we'll go into sources, and as you go down here, you can just see lots and lots and lots of different options. But one of the ones here is DC power. Click on it, and it looks like a symbol for a battery. It's the SI symbol for a battery. And I'm going to click OK, and I'm going to plonk that in here like so. Get it nicely lined up. Now, something I said to you last week, actually I'm very anoracky like this, so I'm just going to tidy up my circuit. I want that over there a little bit. And that there, yeah, that looks nice and neat. Now, the other component that I need inside here, I said to you before, I'll repeat it again, Multisim needs to know what the ground is, or where the ground is. Why does it do that? Because it's doing lots and lots of mathematical computations using Laplace, and I've made a couple of videos on Laplace if you go to the resources. It needs to do its calculations, so it needs to know where the ground terminal is. Now, when you do things inside a laboratory or at home on your desk or whatever, you don't specifically need a ground. You can just use the negative of the battery. But if you do, it won't simulate properly. So that's why you need to add this particular component here. So place component. It's to do with screen resolution. Here we go. So place components, and somewhere down here with the ground. Where's the ground gone? Here we go. So we've got a digital ground. We don't want that one. What's it done with the ground, Mike?
It's normally at the top. I think that one.
So yeah, so it's in power sources. Yeah. So
Yeah, there we go. Ground there.
yeah, you've got this one, which is a slightly different one. That's a digital ground, but that's the one we want. That symbol there. Okay. Click OK. Whoops. Come back. And plonk that down somewhere so it looks neat. And then click close on that. I'm just going to scroll up a bit. That's better. Get it in the middle of the picture. Okay, so there's our circuit, and you know how to join your components together. So you click on the end of the component, click where you want it to join to, click away, click on the component. Don't really like it like that, so I'm just going to join these two together first. Not happy with that. Click on that. I'm going to move this down. I want a neat picture. Move that down and click on that line there and just drag that down a little bit. That's better. That looks more like a circuit, doesn't it? Just drag it back up again a little bit. Experiment. There's nothing you can do that will go wrong. And if it does, just click on it and hit the delete button. And then you can start all over again. Bring my ground symbol back up. There's nothing magic going on here. This is just me trying to be an artist, really. Just trying to neaten things up so they look nice. And up and across, if it'll let me. Sometimes it won't take a very neat path, so you might want to move the components about. But that looks like a nice, neat circuit to me. That looks like it's like it would do in a book or something, right? So 12 volts is a nice number, but I don't know, 12 volts is for cars, right? I like ones divisible by 10, so I tend to use 10, 1, 100.1, those kind of numbers. I'm going to make this 10 volts. Now, what did I do to do that? All I did was I took the components and I double clicked on it. Up came the option on here, 10, and click OK. And you'll notice that change has come into being there. I can do the same with the resistors, so I can double click on the resistors. 1K, I'm happy with that, so I'm going to leave that as it is. 1K here, I'm happy with that, so I'm going to leave that as it is. Good, good. So this is really where we got to last week, and that's why I said I'm not too fussed about the listen again. It's well, that the university haven't put online for us yet. Maybe we'll get that by next Christmas, but in essence, you haven't missed anything. So here we are. What can we do with this? Well, the first thing that we ought to do with this, and I'm just going to have to drag the zoom window out of the way because that's in the way of everything. Just put that down there somewhere. Yeah, that's out of the way. It's nice to be able to see what's going on, but by the same consolation, it's not good when you can't reach the components. So one of the first things that I could do here, and you recall down the right-hand side here, is all your measuring equipment. Just highlighting one. I don't know whether you can read that on the share screen, but that says multimeter, that says wattmeter, and so on and so forth. I'm just going to put, for the time being, down a multimeter and plonk him somewhere there. It doesn't really matter where. Just really recounting or bouncing back to where we were last time. Okay. So if I put a connection, if I put the negative to the positive here, all I'll do is get a negative reading, but the plus generally goes on that side, and that one will go down to ground. Okay, if I double click on the meter, you can see it's already measuring volts, so it actually knows the way I've connected it, and it's predicting that I want to measure voltage, which is fine. What voltage am I going to get out of there, Mike?
6 volts.
6 volts.
Hang on, let me look at the picture. So I was looking at yes,
I changed.
I would have 5 volts.
I changed the power supply.
Snuck in a change.
I snuck in a change. Yes, I did. While you weren't looking. So I hit the play button. So I hit the run button, which is this green one here. My design is now running, and you can see that it's got 5 volts coming out there. Now, Multisim is probably running this at about 1,000 calculations a second and all this kind of stuff. It doesn't need to because the design doesn't change. But rest assured, when I press that run button, the machine is doing some very complicated things. And I'm going to press stop. Okay, I want everyone to get to that point. So I'm going to allow 3 or 4 minutes because I know you've been doing it at the same time as me, so that we've got some opportunity to address any problems that we have. There's nothing new in the Q&A. Nothing new in the chat. So really, where we're going to go after this, I'm going to put an AC source on there, and we're going to see for the first time the use of an oscilloscope. Mike, do you want to tell us what you think or you believe an oscilloscope to be? What does an oscilloscope do?
An oscilloscope is a unit that allows you to measure voltage against time, and so
Right.
so it allows you to draw a graph where you plot as many voltage points as you want over a time period that you choose, and the oscilloscope allows you to automatically change the amount of data points that you want to collect and the scale of the time that you want to use and the scale of the voltage you want to use to quickly allow you to visualize what's going on in a nice and easy to use screen. And it's normally in this day and age, with most of the the circuits that we use nowadays, there's no other way around it because the speeds that are happening, and so quite often you can have a circuit that's running at 100 megahertz, which is relatively slow in today's world of embedded systems. 100 megahertz. I mean, if you wanted to plot something for 1 millisecond at 100 megahertz, and you wanted to draw graphs to represent the voltage, I mean, you'd be there for years, wouldn't you? Just for that 1 millisecond at 100 megahertz.
Yeah.
And the other benefit of the oscilloscope is it allows you to home in on signals within the circuit that you're building, to be able to freeze the oscilloscope screen at a point in time, depending on the signal at your system at that point. So it's like a remote trigger for your camera. And so when that animal runs past it, it snaps it, and then you get that frozen snapshot in time at that moment. That's the beauty of an oscilloscope. And I can say that if it wasn't for an oscilloscope, I would not be where I am now.
That's a nice analogy, actually, the snapshot. Actually, it's not a snapshot, it's a standing wave created by the sampling process of the scope, of course. But that, that's rather a subtlety. But as far as we're concerned, it is, for all intents and purposes, just like photographing something that's traveling really fast. So you've got the waves on an ocean, and you can watch the waves going backwards and forwards. But when you actually take a photograph, you notice that, well, they look like they're fixed. And you can measure the height, you can measure the distance between them, and all this kind of stuff. So Mike's going to bring in, it's not a Rowan and Schwartz, is it?
Do you think I have any Rowan and Schwartz oscilloscopes in this lab? I mean, honestly, this is a Tektronix oscilloscope. I'll turn it on, shall I, and just show some of this, the knobs?
Yeah, go for it, because we're going to be running oscilloscopes and talking oscilloscopes. So yeah, that's a real one in operation before we do a simulated one.
Right, let's see if I can.
Yeah, your camera's too high at the moment. Can you see yourself? Can you see your? That's better. No, that's better. I think it's all right.
Yeah. Okay. Right.
So you've got a test waveform on this one, have you?
Yeah. Okay, so I turn it on down here for me. Which side am I on? Okay.
Now, these things, a number of years ago, a scope of this quality would have cost you the price of a small house. But now you can get them quite reasonably. I don't know how much you pay for this one, Mike, but
this is actually quite an old one. I mean, when you look at this, this is 100 megahertz, 2.5 gigasample a second. So when this was released, it would have been in the £10,000 area, but you could probably pick this up for £2,000 now. But when you look at some of the other things in this lab, like there's a 2 gigahertz, 10 gigasample a second scope in the back there with all kinds of analysis packages put onto it, and that's £50,000 plus on that one. It actually runs Windows as a scope.
oh dear.
I don't want that. Yeah, they've actually done something to Windows so it doesn't crash as well.
Oh my word, that's clever.
That. But there was another scope up there which has got a spectrum analyzer embedded in it. I mean, that's again very, very expensive. Okay, so we can see a picture here. So what we have here is if we imagine this is a graph, so we have our x and our y axes, and along the x axis down the bottom here we have time, and along the y axis we have voltage. So if I press our default button down here somewhere, which I believe is down here somewhere, isn't it?
It's difficult doing things in reverse, isn't it?
I can't see it. There we go. Default setup. There we go. So if I click this, so we'll start in a basic mode. Let it default up. So what this is going to do for me now is this is telling me down here, as we can see, that I have one channel, this yellow channel, and it's currently set at 100 millivolts per division. A division is one of these squares. Can you see all those tiny little squares without the
Yeah, we can. There's a bit of reflection on the screen. That's a better angle, Mike. Yeah. So each one of those running horizontally is 100 milli, which is 1,000th of a second. So it's 100 1,000ths of a second, each one of those square boxes. Yeah.
Yep. And so if I get a Oscilloscope Pro, typically this is a 4-channel oscilloscope, so that I'll be able to put 4 series on your graph.
Yeah. So you can look at 4 things at the same time inside a circuit on the same screen. So they're just superimposed onto the same screen. The ones we see in simulation are either 2-channel or 4-channel, and this is a for real 4-channel one.
I plug my probe into channel 1.
You've got a test point on that scope, I assume.
There is a test. It's what we call a compensation calibration point,
which is just basically a test point to make sure the scope's working correctly.
Okay. So what we can see now is I have what looks like 2 lines up here, but it's actually not. It's 1 line. It's just refreshing very, very fast. So now this is an example of me not having the speed matched to the signal that I'm looking at. And the easiest way to do that now is like I explained earlier, there's a trigger where you can say there's another signal on my circuit or the signal that I want to look at. And when an edge changes, i.e. when an edge falls or an edge rises, stop my oscilloscope. So that's what I'm going to say for it to do now. So I'm going to use this trigger over here. It's all very difficult when you're trying to do it from the other side.
Yeah, logic are never easy.
There you go. And so it's asking me, I'm triggering off my channel 1. And as it says here, I'm going to trigger on a rising edge. And now I'm going to set my trigger level, which is
everyone, you'll be doing this in simulation in a minute. So may not be clear what Mike's doing, but don't worry, you'll do it for yourself in a second.
So now, I've just told my threshold there to say that if this pulse rises above this line, then stop my scope. And that's it. That's what's happened.
Just alter the time base, Mike, so we can see a repeating waveform.
So now I'm going to change the scale of my x-axis and make it look at a larger segment of time. So I'm looking at a bigger segment of time, so I can see more of the speed of my signal within that window.
So how often is that square wave going up and down on that test point, Mike?
That's a very good question. Let's first of all, let's position it so we can see that our trigger point is here. And we can see at the moment the 1 division is currently set over here to 400 microseconds. So we've got 400 microseconds on the x-axis, and it's taking just over 1 division. So it's just over 400 microseconds. But that's not really the best scientific answer to that question, is it? We want to know exactly the frequency of that pulse. So the great thing about an oscilloscope is what we can do is we can add a measurement. So we can press this measure button here. And what that would do is that would bring down a whole load of add measurement options down here. So we press add measurement and we say a measurement on our source 1, and we choose what type of measurement we want. And I'm going to ask for a frequency measurement like that. And I'm going to press OK. Yep. And then I'm going to turn my menu off. Now down here, now you can see we have a frequency here. And that's telling me that I'm currently running at 1.119 kilohertz. Is that kilohertz? Can you see that? Can't see it, Bobby. Kilohertz.
Yeah, well, we can't see it, Mike, but we can see the waveform.
So down there, it's telling me the frequency of that signal that I'm looking at.
Yep.
And
so a pretty wonderful piece of kit when you think about it. So you're changing the amplitude there now, aren't you?
Yeah, I'm changing the scale of the y-axis, the voltage scale. Oh, sorry, it's gone into zoom mode. Sorry. No, I'll keep it simple. So I've just maximized the dynamic range of my oscilloscope so that I can suit it to view the signal that I'm looking at and get as much detail out of that signal as possible.
Yeah. Okay, that's brilliant. Well done. Thank you for that. So, a magic box that lets you see waveforms, and it lets you see waveforms that travel or change much quicker than your eye could possibly see it. We can go up into the realms of millions of cycles a second, and we can plug an oscilloscope in and we can see that waveform as if it were a wave on an ocean. We can just stop it momentarily and have a look at it. And that's enormously useful. That's the beginning of being able to work with AC signals. Now let's go back to our page. Hang on, I've got to share screen. So we'll go back to our diagram here. Now what we have here is a DC multimeter, just the well. It can measure the average AC, which is what this setting is here. But we're not interested in that for the time being. But a multimeter is primarily designed to measure direct current. In other words, batteries. Now, batteries, I was going to say don't change with time, but they do if they're charging or discharging. But this 10 volts here, for all intents and purposes, will always be 10 volts. It's not going to go 10 volts plus, 10 volts minus, 10 volts plus, 10 volts minus. It's going to stay exactly the same as it is. Now, we did last week the potential divider. R2 upon R1 plus R2 times V in is what V out is, and this is V out here. So what that means is that we can completely predictably predict what's going to come out of here for a DC waveform. Okay, so you can play about with these ratios. I'll just do one like we did last week. So let's make this now 2K. And the smart money would say that you'll have more voltage dropped across R2 now and less across R1. So I would expect the voltage to go up between 5 and 10 somewhere. Let's see if we can do that. And the smart money's right. Look, so the voltage here has gone up because I've increased the size of this. And if I decrease the size of that, so I do 0.5K, we can see a similar kind of effect but the other way. It doesn't like it because I've got the simulation still running. Click OK, stop my simulation, start my simulation again, and you'll notice that it's gone down below the 5 because most of the voltage is dropped across this resistor and less is dropped across this resistor. Okay, V out equals V in R2 upon R1 plus R2 as given on the 721 page and the little bit accompanying theory, which is on the loads of videos on here, by the way, under the module resources. Okay, so here's just some that I did for you last week, and lots more I'll do as time goes by. But have a look at potential divider theory part 1, potential divider theory part 2. Some of you might say, what on earth has this got to do with the assignment? Well, a lot, because what it's doing is it's giving you the basic skills necessary to do your assignment, and we're just using some very simple examples. Okay, so that's why we're doing these somewhat trivial examples. I know some of you in the group have done no electronics whatsoever, and others in the group will have done a considerable amount, but just bear with us, the ones who do know the operation of the scope and so on, because we will surprise you from time to time, especially when we start to go into Laplace and low pass filter analysis and so on, which is where I hope to get today with a bit of low pass filter analysis. Okay, so there we are. That's DC. So now let's get rid of the multimeter. So you know what a multimeter is for, but let's delete it for, I think. We don't need it anymore. We've got to stop the simulation. So goodbye multimeter, we'll see you in the future. Let's put this back to 1K. And let's introduce, oops, I've got to say, okay. Now let's introduce, I'm sharing screen, aren't I? Yes. Function generator, wattmeter, oscilloscope. So I'm going to introduce an oscilloscope for the first two. You saw it last week, but we didn't actually do anything with it. So this is a symbol representing what Mike had on the table there. There's only two channels you can see, channel A and channel B. And I'm going to wire up channel A onto these points here. Bingo. Job done, right? So double click on the oscilloscope. What's going to happen, Mike?
Let's have a quick look. Yeah, you need to share your screen, John.
Oh my God, I thought I had. I asked people whether I was.
Yeah, they're just coming in to tell you you need to share your screen. There we go.
You might please tell me if I forget to do that. It's just so easy to do with all these windows open. So what's going to happen with that circuit, Mike? So I've put the oscilloscope in there instead of the multimeter now.
You've put an oscilloscope in there, so you're at a good point of measurement there. So you've got your positive going into the A channel there. So you're going to see a single line. What do they call that in medical terms? A flat line. A flat line.
Yep.
You're going to see a flat line that's measured at 5 volts above ground. So it'll be on the Y scale. The flat line will be at the 5 volt points, and it won't change for the duration.
Okay, so my patient here will be dead, unfortunately.
Yeah. It's a DC. It's what we class as a DC output will be going on there.
Okay, let's see if you're right. I think you probably are. So if we run that now, and look what we have here. So this line in the middle is 0 volts, and this line here is according to this scale here. So channel A scale, this is in the Y direction, the upwards direction, 5 volts per division. That's what we have here. I could change this, couldn't I? So I could say, let's go for 2 volts per division. And you notice that the line has moved, but the measurement hasn't changed. It's still 2, 4, 5 volts. And if I put it on 1, it's obviously off the screen, so that's no good. But I put it back on 5, and you can see that I've got 5 volts output. My scale, so each one of these squares here is 10 milliseconds running across here. So this is 10, 20, 30, 40, 50. So that's a second from one side to the other. No, 100 milliseconds from one side to the other side, or 1/10 of a second from here to here. Clearly that wave isn't going across there at that speed, but that's just because it's being simulated, nothing more. Okay, same reasoning as before applies. So if I stop my simulation and I change the size of the resistor, like I did before, to 2K, and I apply it, and now I run the simulation again, look what happens. My output is now 6.6 volts, like we saw before, and you can see that you can actually use the oscilloscope to take these measurements. So in a way, what the oscilloscope is being here is it's acting like a multimeter, except I need to look at the screen and look at the straight line to be able to work out what that output voltage is. So a multimeter, or the majority of cheap, easy to use multimeters, can't measure AC very well, but in actual fact, an oscilloscope is good at both jobs. It can measure DC values, and as I'm going to show you in just a second, it can measure AC values as well. Okay, I'm going to stop my simulation. I'm going to unshare just for a second, and then I'm going to wait and just see what happens from the feedback. If we get no feedback, we'll proceed. Right, so we've got, you're not sharing a screen yet. Thanks very much. I think I've, yeah, thank you. So Mike's going to remind me. Mike's going to.
Yep. They all come through exactly the same time.
Yeah, I know. Mike's got a big hooter at his end, and if I don't share screen, he's going to and raise the alarm. Okay. Yeah, sorry about that. You didn't miss anything, of course, because it's still on the screen there. So you're going to build that for me. Hopefully you will have been doing that as I'm doing it, because I'm deliberately taking it fairly slow for you, and you should be able to get that circuit running. Okay, so where are we going next? Well, we're going to put an AC source on there. We're going to put a thing that makes waves. Well, how do you make waves? Well, baths are sort of fading into the past, really. I mean, most people have showers nowadays, but you get in the bath and you get in there too quick or get out too quick, all the water slops over the top, doesn't it? So that means that you getting in the bath has created a wave. But you'll also notice from that wave that it slops over the top of the bath. You think all your problems have disappeared. It goes up the other end of the bath and it bounces back and then it slops over again. So a wave is something that once you've created it, it doesn't just stop straight away. It carries on oscillating for some considerable time. Now, on an AC signal source, what we can assume is that that wave remains the same over all time. So if I put a wave in which is 1 volt peak to peak, it's going to be 1 volt peak to peak forever until I tell it to be something else. Now that's quite a nice place to be, because it means we have a nice steady waveform that we can inject into our circuit. Can we do a quick recap on setting the oscilloscope? Is a question here. Are we talking about the simulated oscilloscope or the real oscilloscope? I'm not sure there's any value in doing the real oscilloscope because we just simply can't get the quality of images which we're looking for. So I'll assume that that Q&A on there is about the simulated one. So yeah, let's go back to that. So
I think we could point out some great videos at this point, couldn't we?
oh yes, most definitely, most definitely. So if we go onto YouTube, and we type in Wood-O Woods, we go to my TV channel, and you can see the recent uploads and so on. But if you go into playlists, and you can see lots of stuff in there. But C7212020, have a look at me flying my paramotor. But have a look at C7212020, and oh, I don't want to play them all. I just want to view them. Hang on a second. So view full playlist, and you can see down here there's lots and lots and lots of videos. Someone was asking me at the weekend, I even work at the weekend, you see, how they wanted to get on with their assignment, but they didn't know how to build a PCB yet. Well, if you want to get that far ahead, then have a look at these videos. Ah, I wonder where that video for that pulse motor has gone, Mike.
Oh, it's there, is it?
Yeah, let's just have a quick watch of that, shall we? So you didn't blow your hooter at me, did you?
I can't able to run the circuit. The option is disabled. Last circuit could also to run, but this is not. If the option is disabled, is it because the last circuit is still running?
Yeah.
You could only have one running at a time. So if you've got multiple projects opening up in Multisim, and make sure they've all stopped and that you're only running that one simulation. Also, make sure if you can't run your simulation, make sure that all your wires are properly connected and that you have a ground.
And if that fails, we'll get them to share screen in a minute. But the hair test, remember that? We had a separate one on instruments, didn't we? Here we are.
Yeah,
Electronic lab.
I can't seem to.
Electronic lab instruments. There's a nice one on there about oscilloscopes, scope probes, all the rest of it, taking measurements on oscilloscopes, all the rest of it. So this is on Wood-O Woods and on my playlists, and you've got electronic lab instruments, Multisim tutorials, so that you can see it from a different perspective, not the one we're doing now, but it's pretty much the same content. the assignments, everything that you'd ever want, you can find there. Okay, sorry, Mike, what was the query?
So I couldn't answer the Q&As, but I've just lost it. No problem.
So that's the recap on the scope. So yeah, thank you very much. So yes, now I understand. That's great. Fantastic. We're not getting anything else, and we've gone past the 5 minutes that we were going to allow. So I suggest we move on to the next thing. Mike, I'm sharing screen. Look, green button. Share screen. Share.
Yep,
Okay.
definitely sharing.
Definitely sharing. Good. So back to the VM Horizon server, and maximize it. So just a quick recap on the things that are going on here as well. So the scale, which is the horizontal one, 10 milliseconds per division, I can change it. 20 milliseconds, 5 milliseconds, I can change it to anything I want. And this one is in the Y direction. It's 5 volts per division at the moment, but I could go down to 2, and but I need to be very, very careful that I still hold it on the screen. So I've got 20 volts per division. Obviously the line fits down into there, more 10, and so on. Okay, so it's just, how do you choose those numbers? You choose it so that you view the waveform the best. And you'll see that better when we inject an AC signal in a second, okay? So that's DC, that's high school stuff, that's baby stuff almost. What we're interested in is alternating current. This is grown-up stuff. This is degree level stuff. This is career facing stuff. Signals, in its simplest sense, a DC waveform like a battery is an AC waveform. It's just an AC waveform with 0 frequency. And that's a much more grown-up way to view what waveforms are. So actually, this is an AC waveform with 0 frequency. Now, let's, so the simulation is stopped, good. Let's click on this and just delete this component. So now what I want to do is I want to place component, and in this particular case, I want to put, previously I put DC power, right? So that was the battery. Now I'm going to put AC power. Now look at what that looks like. That's a fairly standard representation of an AC source. And that AC source has infinite driving capability as far as voltage is concerned. There's no parasites on it. There's no parallel resistance to it. There's no series resistance to it. That circuit there would drive an infinite amount of power if we asked it to. We're not asking it to, because we're just feeding it into effectively 2 1K resistors. So click OK. Bring this across here and put it down, lay it down. Close it. Let's wire it up. Wire that one to there. And you can see at the moment it's 120 volts RMS. What's RMS, Mike?
Root mean squared.
Yeah, what does that mean as far as something is concerned there?
It's the average value that's coming out, because when you have a wave that's that's varying in current, then obviously there's times where current is sunk as it is sourced.
Yeah.
And so therefore you need to create an average, as it were. I think there was that, isn't it 70-something%? Isn't there a multiplier for it? I can't remember what it is.
Yeah, so 0.7071, so it's 1 upon root 2. But really where it comes from is when you have an AC waveform that's going up and down, obviously there's certain times when it's sort of 0, and there's other times when it's at its maximum. So actually what it is you've just ironed out the peaks. It's kind of, RMS is what you get if you smoothed an AC waveform. In other words, it's kind of the DC equivalent of what's in the AC. That's all that really means. You don't need to know that for these purposes. That's just, so we're going to put in this particular case, as I say, I like 1s, 10s, 100s, and those kind of things. So I'm going to put in 10 volts, RMS, no offsets. What frequency shall I have? Well, let's go for mains frequency. So let's go for 50 hertz. All the rest can remain, all the rest are unimportant for what we're doing here. So 10 volts, RMS, and a frequency of 50 volts. And we click OK. What do you expect to happen here, Mike?
Oh, you've got a 1K and a 2K on there, so you're going to get a reduction. You're going to see a wave on the.
No, I didn't mean to do that. It should have been 1K. I'm just going to change that to 1K. What do you expect to come out now?
Just some attenuation on a wave is what I'd expect to come out.
That's what you would expect, yeah. We've got RMS here. It won't let you do peak to peak, but it's okay, fine. So, ready for this? The magic run button. And oh. Why haven't we got a standing wave there, Mike?
Sorry?
Why haven't we got a standing wave there?
Oh, you need to put your trigger on.
Okay. So I go over to the trigger here.
Yeah, just lift that level up a bit there.
Yeah. So tell me what that's doing. So at the moment, what I see is a waveform. So that would be like standing at the beach, watching the waves crashing onto the shore, right? So it would be moving and I wouldn't be able to see what the wave actually looked like. I'd just see a melee of waves, all one over the other. So what does this trigger level do then?
Well, that lifts up the threshold at which you want the voltage rise or fall to stop the oscilloscope. So if you imagine the trigger is a point on your y-axis of voltage level, and you're saying that if the measured voltage either passes this point upwards or downwards,
yep,
at this threshold, then freeze my screen for a predetermined duration, which is normally, about a second or so, and then it will carry on.
Okay, so it's a point of reference. So if I bring the trigger level up to 1 volt, still not standing. Why is that?
You need to turn it on as well. You need to change it on the things that put normal at the bottom. Yeah, normal.
Yeah. There we are. And I think actually that won't have much of a bearing, even if I do have the trigger level at.
No, it should just change the phase now. If you change the trigger level now, it should move the phase of the signal.
Yeah. Okay, but what we see there, we can see a waveform. Yeah. Let's take the other output. So this is channel B, and let's have a look at the input. What does the input look like? Well, this isn't going to be a very neat bit of wiring, but I'm going to go up around here. Oops. Doesn't like that. Let's escape that. Oh, I'm still running the simulation. I need to stop the simulation. I'm just going to route round here. Not a very nice piece of wiring, but click on there, and this one down to ground as well. And now I should have 2 waveforms on there. So on channel A, I should have the output waveform, and on channel B, I should have the input waveform. Let's run that. And there you can see the 2 waveforms. You can see they're in phase because they cross the 0 and they have the maximums at the same time. And you can see that one of them is exactly the same as the other. Sorry, one of them is exactly half the size of the other. Okay. So under those circumstances, we could diagnose this circuit because we could say what's going on in the input compared to what's going on in the output. And if we didn't have anything on the output, we could use the oscilloscope probe to work out where our circuit had become broken. That's what we could do quite effectively on that. Okay, so that's using both channels at the same time. Let's stop that. Let's get rid of that because that just looks untidy and cumbersome. And now we're going to start playing about with frequency a little bit. So at the moment, we've got 10 volts RMS 50 hertz, or 50 hertz up and down 50 times a second. That's unbelievably slow. Unbelievably slow. Let's go for something a lot more realistic. And, well, let's just start at 1 meg or 1 million. And let's just see how the circuit copes with it. Shouldn't make any difference at all. Now, what's going on here? Why is this doing this, Mike?
Yeah, that's because your time base is so slow
Yep.
that it's trying to build up the signal over a much longer period of time.
Yeah. So
Because,
this division here is 10 milliseconds, but I'm running at 1 million times a second. So actually what I need to do is I need to speed things up a bit so I can actually see the waveform. See, look, it's just starting to see the waveform. See that? Because prior to that, it just looks like a blob because those lines are so close together. But now watch what happens as I speed it up more and more and more. Suddenly, I can see that individual waveform. Yeah. And the period there is one across the frequency. So this point here to this point here is 1 upon 1 million. 1 upon 1 millionth of a second. So you start to see the power of oscilloscopes. We can see very, very, very small amounts of time. And we can start to diagnose circuits quite accurately. Okay, I'll give you 3 or 4 minutes to identify any problems on that. Like I say, we don't want to leave anyone behind on this. It's all about kind of the journey rather than the race. Okay, so where are you on that? Let me know. I'll stop the share now. Most of you will have done that.
it's fair to say, isn't it, John, that if you could choose one piece as an electronics person, if you could choose one piece of test equipment to carry through your career with you, it's going to be the oscilloscope, surely, even more than a multimeter.
Yeah, yeah, it's kind of the shovel of the electronics world, isn't it? Really, it's difficult to imagine. It's difficult to imagine an industry without it.
It's the tool that's worth getting to know inside out, I think.
Yeah, yeah. They're all different, but they all do basically the same. You've got amplitude, you've got frequency, you've got phase, you've got the ability to trigger, and you've got the ability to measure the distance along the horizontal and the distance along the vertical. And beyond that, most oscilloscopes do exactly the same thing. It's just the buttons might be in a different place. But I encourage you to go to that Wood Woods YouTube resource that we put in place last year. It's still current now. It's not out of date. And just go on there and you can see some nice demonstrations of using bench-based equipment. And you can get some kind of idea for it. Should you buy yourself one? If you know, sure that you want to get a career in electronics, it's difficult to imagine doing it without. I've got, I do a bit of electronics here in my workshop. I've got 3 oscilloscopes in my workshop. I'm going to ask Mike the question, but I think it's probably going to take a couple of minutes to count them up. How many scopes have you got in your workshop?
Yeah, you know, I mean, here alone, I can see what 1, 2, 3, 4, 5, 6, 7. I can see 7 in this room alone. And then I've got, you know, some old ones up in the garage. There's some portable ones back, you know, for going on site. And yeah, I mean, I couldn't survive without one. Honestly, it's the go-to tool
Yeah.
for all measurements. And
Yeah. So magic bits of kit, really. I am aware that from Rapid Electronics, just before they shut the outlet up there, you can still get them online. But I saw my first sub 100 pounds oscilloscope up there, and I was a bit skeptical about it, and I went and had a look at it, and it actually looked okay. I mean, it didn't go to phenomenal frequencies, but for a general purpose tool that you might have in your home workshop or something, under £100 sort of puts it into fine Christmas present range, doesn't it? If the family are looking for something to buy you or something.
Another very good thing about oscilloscopes that we take for granted now is their ability to document what you're looking at, what you're doing by screenshots and snapping, that you can then import that picture directly into your projects or data sheets or whatever. When I started out, and I'm sure you can remember this as well, is we had analog scopes at that time with cathode ray tubes. And there weren't, the data connections. I mean, you were lucky to have a GPIB module at that time to offer a little bit of automation. But if you wanted to take the screenshot, you actually had a camera, a physical camera that clips over the cathode ray screen, actually covered up what you're seeing. It's like hanging a camera on your TV, and then you press the button and you took it off again. And that was your documentation, So many things we take for granted now.
Yeah.
Consider that them days.
Yeah, and we still have one in the lab, and I stopped it being thrown away. We had a very, very, very early digital camera with a 3 1/4 floppy disk in it. And on the MSc course 20 years ago, we were using that to do exactly what you're saying, Mike, because the scopes didn't have USB or networked drives, and it was the only way that people could get things for their assignment was to literally take a photograph of it. We've had one just come in, how to stabilize the waveform on the scope. That was, we did that, just share screen again. So that was the issue down here where your trigger should be on normal on this, and you should get a standing wave. So go to normal there. The fact that it's going across the screen and flickering, you're not going to get away from that because it starts and then it finishes. So that's just part and parcel of it. But they should be on the normal setting here. You could hit the single and you would just get one shot across the screen. That will clean it up, but it's not running, if you see what I mean. So that's just one pass of the screen. So no flickering, there's your waveform, but it's not running until you go back to normal, say. Okay, hopefully that answers that one. This works quite well, actually, Mike, doesn't it? So using the AC voltage, the graph of the oscilloscope is just vertical lines. I don't seem to be getting the wave. Isn't the time scale that needs to be adjusted?
This is the trigger that needs to be adjusted on this one. It's just vertical lines. Now that's a schematic problem. If you've got just vertical lines, then yeah, it's possibly the time scale is way too small. If it's just a vertical line, it's not moving even over a long time.
Well, let's go back to this so that they can compare settings. So, why did I stop sharing? So here we are in the settings. So make sure you've got your waveform here. So 10 volts RMS, 1 megahertz, or whatever you want to put on there. Your trigger level here, make sure that's set to normal. Have a look at your scales on here. Beyond that, I think we're probably going to have to allow a share so that we can have a look at it. Q&A is coming in. Let's stabilize the waveform. Yeah, I think we did that one.
Measuring
current. Mike, I'll hand that one to you, I think.
Well, you can measure current with an oscilloscope. It's just you need to prepare the measurement before you make it. As you know, current is normally measured in series, and it's not advisable to connect a circuit up to your oscilloscope in series because you can't really control what you'll be flowing through the front end of the oscilloscope. It's just not advised. So what we do, if you blow the front end of the oscilloscope, you get a bill for many thousands of pounds. So it's not advised to put voltages that you can't control or currents that you can't control through the front fascia of the oscilloscope. But if you want to measure current with an oscilloscope, you can either buy a current probe that uses a very highly calibrated field effect sensor in the front of a clamp that you can clamp around wires, and then that will then condition that signal coming into the oscilloscope and give you a current measurement. The second way is to turn the current that you want to measure into voltage, which is probably the most common way, although it will involve some kind of resistor or something to be able to have a point where you can monitor the current, and it will affect the circuit that you're monitoring. A field effective array won't affect the circuit you're monitoring, but any kind of current measurement, and let's be clear about this, not a problem in an oscilloscope, any kind of current measurement made on any circuit will influence the measurement it's making, because it has a burden voltage, and it has to, what's the best word to do this? It has to actually consume some current to be able to measure what it's trying to measure.
It has to pass through the device, doesn't it, Mike?
Yeah.
And the way that you generally measure current for these kind of purposes is you cause a volt drop across something. So a way that you might infer current is to put a very low value resistor in the circuit and put the oscilloscope across the very low value resistor, and obviously turn the gain right up on the oscilloscope, do your calculation according to Ohm's law, and then the voltage waveform that you read off on the scope is actually the current that's flowing. So you can infer it by an indirect measurement by a volt drop across a component. I'd like to move on. I'm not sure whether it was RX20884. Have you managed to get your waveform?
So is someone still trying?
Okay, well, let's try something new. So let's promote them to panelists and let's have a look at what they're doing. RX20884. Okay, so you're panelists now. You want to share screen with us? We've got a share screen option at the bottom. So you're on panelist. Can you share screen with us? You have that option?
Yes, just 1 minute.
Okay, share screen then.
It says host disabled participant screen sharing when I try to share screen. I don't know why.
Because
you need to do that your end. I think the only people that can share the screen are the what you done to me last time to share my screen, because I had that same problem, and I think you had to make me a coordinator if I remember right.
Yeah, clearly that's not practical. So let's promote you to co-host. Okay, can you share screen now? Okay. Right, pull that oscilloscope to one side for me, will you? So you've got 10 volts RMS. We need to see the whole circuit. That looks right. Everything's connected. Plus minus 50 hertz, 1K, 1K. I can't see anything wrong with that. Can you, Mike?
No.
Okay, so bring the scope, so now we can see the oscilloscope. So we've got DC going across there.
2 volts to do, 5 volts to do from B, and you are DC, Y, and T. So, and it's running at the moment, is it?
Press the run button.
Okay, you're off the line a little bit there, aren't you? So you're looking at 2 microseconds of division. 2 volts to 5 volts.
We're on DC, but that shouldn't make any difference. We've got the amp setting on there. So A selected.
Yes, it's so it's got a voltage on there. If you put it into AC mode, John, will it settle down on the 0 point? It should do. If you put it on AC mode on channel A, yeah, press
Yeah.
that button just for me a sec. Just make sure that see that's not even reset into 0, is it?
No,
On that
so
one there?
there's a problem with the circuit. Go back to the circuit. Let's show us the circuit again. We're at 50 hertz. What's the time base on that?
There's something, yeah, I think. Right, what you want to do, I think, is you want to just delete your oscilloscope completely. Take your oscilloscope out a second. Yeah, remove it and close the window from it.
Hit the delete. Click on the oscilloscope. Hit delete.
That's it. And okay, right. Now let's so we've got a 10-volt RMS, 50 hertz, and there's no phase, 1K, 1K. So we should obviously read a lovely signal. So put an oscilloscope back on there. Okay, and then wire that positive up to that point. Yeah. I will say now, occasionally, and we saw this on multiple years, occasionally Multisim does get in a twist.
Yeah.
And the only way of clearing out the problems from simulation is to close it and reopen it.
But Mike, there's been quite a useful tip coming from someone that they said they increased the frequency and it went away.
Okay.
So connect that point to ground.
Yeah.
Click the run button. Well, yeah, obviously open your scope.
Okay, we've got defaulted scope at 10 milliseconds now. It's looking better. There we go. Yeah. So I think what was happening before, for some reason your scale was down in the microseconds and it may have been running way too quick, but it may, sometimes with Multisim, when you're running too fast, the actual screen of your oscilloscope becomes smaller and smaller and you end up with just a chunk on the left-hand side. I'm sure you've seen this before, John. What's going on there, I'm not sure, but you may have hit something there. But we should have been in a milliseconds on the time scale, and now it's looking perfect.
Yeah, and someone else had the same thing. They managed to solve it.
Thank you, sir.
No problem at all. Pleasure. So we've got to undo you, otherwise things could get a little bit confusing.
So from Roisin, where you mentioned that you increased the frequency, I'm assuming that did you increase the frequency of your AC supply, or did you increase the frequency of the oscilloscope watching it? The source. So you increase the frequency of your AC supply. So you've actually not got the same answer that everybody else has got, because what you've done there is you put a piece of measurement equipment on your circuit to measure a signal. You didn't like the measurement, so you've adjusted your circuit until you've seen a measurement, which is the opposite way around of how we want to go. We don't want to change the signals on the circuit. We want to change the measurement system to see the signal that we're seeing. But the point that you made, that the frequency was the problem, is correct. It's just we should have changed it on the oscilloscope, not on the source.
Yeah, but there's been a lovely bit of deduction there, Mike. That you get something that doesn't. And firstly, all credit to the young lady there that she knew that the output waveform wasn't the correct output waveform, and also credit to Roisin as well, because the person realised that it wasn't doing what it should do. So have a play with the numbers. I mean, we're only talking a simulator here. There's not going to be a massive explosion if you inject 500 volts and reverse biased it. It's just not going to happen. It's a simulator. So the worst comes to the worst, your design's going to crash and you're going to have to rebuild it. But that is the absolute worst comes to the worst.
Yeah.
Okay, that's good.
The way forward, isn't it? Play about. Just play about.
Yep. One of the brilliant things about simulators is the zero cost associated with the components and the almost zero cost in time. So how long does it take to draw a circuit? Well, I don't know. I can draw quite a complicated one myself in you know, half an hour, that's a blooming complicated circuit. Well, if I had to build that on breadboard or, you know, rat's nest it or whatever, I mean, that would be several hours investment, time investment to do that. So I would be very conscious about damaging it, but not under these circumstances. Just feel free to have a play. Okay, we're going to run for about another 10-15 minutes, and then we're going to have our 10-minute comfort break. But I'm just going to share screen with you. I'm pressing the share screen button, Mike.
Doesn't,
Okay.
yeah, it looks good.
That looks good. I left my simulation running, which is a bit silly because that could be using up your RAM and everything. But there's my waveform. I can stop it. We all know that if we change the ratio of this, just like we saw before, the amplitude, the peak, which is the top line here, is going to change in amplitude exactly the same way as the DC did. Remember before, R2 upon R1 plus R2 times V in, the equation still applies even though it's AC. The rules are the same for resistors. Okay, notice the little bit I added on the end there. For resistors, that's true, but it's not true for reactive components. Now, reactive components are things like capacitors and inductors. Okay. Now, just done doing the share just so I can talk for a little while. Actually, no, I do need to share because I need to show you where there's a nice video resource for this. I'm minded to play it actually. So we've got all these resources down here. Intro to AC analysis. Let's just see how that one runs, if that runs okay. Okay, just watch this one for a few minutes. In this video, we saw that a capacitor would block DC and an inductor would pass DC. Direct current, frequency equal to 0. Okay, something quite profound I said there, but let's just revisit that. A capacitor, and let's go back to my screen where I can see everyone. A reactive component, a capacitor, has an impedance called XC equals 1 upon 2 pi FC. That's the equation, the defining equation for a capacitor. It probably is easier if I find that video on here that I made the other day. Yeah, this is the one that I intend. Just watch this for a few minutes. So that's fine, and the DC world is really something which tends to be taught at high school. Why? Because life is considerably easier at DC, in other words, like a battery, plus and minus, it doesn't change over time. But life gets really interesting where voltage and current change as a function of time. In other words, they're a waveform. And an alternating current will have a period and it will have a frequency which is equal to 1 upon the period. What that means is that I can increase the frequency of the AC waveform. In other words, if we assume that's a relatively low frequency, we can make the frequency higher by having more cycles per second. And obviously that's measured in magic hertz. And we can say how many cycles, that's a cycle. And let's pick the color and hope it comes out. So a cycle is from this point here, this point here. So the same point on the wave, basically. So how many of those points pass per second That's the number of cycles in hertz. Okay, fine. So let's go back to the thing that we did originally. And so we've got a voltage source, we have a capacitor, and we have load. We have an AC signal here. What happens in this case is, obviously when this goes plus here, that's going to go plus here, it's going to induce a little negative sign on the other side of the plate. And as this goes minus here, it's going to go minus here, which is going to follow a little bit of plus on the other side of the plate. So the plus and the minus, which is happening on this side of the plate, is also going to be a plus and minus on the other side of the plate, even though there's an air gap between them. So that means AC current is going to flow through the capacitor. So we're actually going to have real current flowing through that capacitor as the other side of that capacitor goes plus minus, in the same way, but out of phase, but in the same way as it does from the original AC voltage source here. Now, one of the equations, which you may well have seen in high school, is the XL, which is the inductive reactance of the capacitor. In other words, the equivalent resistance it has is equal to 2 pi for the inductor. Getting ahead of ourselves a bit here. I'm just going to gloss through that for the moment. So XC is equal to 1 upon 2 pi C. That's the one for the capacitor, that's the one for the inductor, but I've just taken that out because we do capacitors first. Now, what does that tell me? What that tells me, so this is equivalent resistance. Or impedance. So alternating current.
You showing the screen, John?
So
Screen
I
share.
like to change the capacitor, that doesn't change for the experiment.
It disappeared or something. Does it turn itself off or something?
So what does that tell me? So that as I get big, it shut itself off, did it, right?
Well, you know, you press the button and it never comes eventually, I think, is what happens. You get the dot 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 coming up,
Right.
and your face appears.
Oh. Okay. What I'd like to direct people to is
Okay, we've still got a few oscilloscope problems here now. We've got
okay, let's deal with those. What I'd like people to just have a look at is Intro to AC Analysis. I'm just going to share screen with that. Yes. What I'd like you to have a look at is this Intro to AC Analysis video. Remember, these are all other, this is the main page in 721, but it's all under the, this is my mouse playing up there. It's all under the module resources, okay? So down the bottom of the module resources, you've got Intro to AC Analysis. I'd like people to have a look at that. I'm obviously going to deal with the content of that as we go through when we do our simulation in a second. But there's some nice theory here. So anything to do with capacitors, inductors, low pass filters, etc. There's some good videos here which should bring you up to speed on the theory of what we're going to do in the simulator in a minute. Sorry, Mike, let's go to the
so we've got TA20116 is still having an oscilloscope problem. Maybe they'd like to share their screen so we can try and find out what's causing it. Quite often it's good to see somebody else's problems from a working point of view, because you kind of get an insight as to what potential problems you might hit, even if yours is working. So it might be worth I seem to have a lag on the chat as well. It comes through in bursts. Is that
Yeah.
normal?
I'm not showing TA201116 on the.
TA20116.
Yeah, they're not showing on this on the panelists,
Really?
on the attendees. They're not in the list.
Have they left or because he sent a message at 10:34.
Yeah, no, he's not on there.
Okay. Okay.
Just respond to the mic, tell them we're here, ready and willing. Okay, thanks. It was shared. We just had a technical hiccup with the Panopto there, so just bear with us on that. I'm still not seeing any anything from TA whatever.
No.
All right, perhaps they'll come back to us in due course. Q&As are up to date, Mike, so I'm going to go ahead and just run this simulation now with a reactive device, which is going to be the capacitor. A little bit of explanation. We'll generate our first Bode plot, and then we'll move into a comfort break after that. Do you think it's a good plan? Okay, so going back to share screen and going back to the VM. Who's beeping at me? I think it's my VM making Windows type of noises, which is annoying. Okay, so there's our circuit, and we've got a signal generator on there, and we've got two resistors. These are not reactive. A reactive component changes its impedance according to frequency. That's what a reactive component does. The video that I was trying to show you just now on Panopto, that I would be grateful if you could watch, explains that there's, for capacitors, the impedance, or effectively the resistance, the AC resistance, is 1/2 pi FC, very fundamental equation. And for an inductor, the impedance is 2 pi FL. Now, what do you take away from those two equations? You take away from those two equations that their impedance, or their resistance, changes according to frequency. It changes according to frequency. To see a Q&A. Quite a complicated one coming there on the Q&A, Mike. Do you want to?
Yeah, I'm on it.
Just take that one on while I carry on the explanation. So what happens in this circuit if I change these non-reactive components for a reactive component? Let's try it. So let's hit my resistor here. I hit delete, and it disappears. Very dull circuit there now. What I want to do is I want to place a component. And that component in this particular case is going to be a capacitor. So I go to basic, I go down, I select capacitor, I click OK, and here's a capacitor. Now, I want that capacitor to fit in here, so I need to rotate it, right? So I click on it, I click rotate 90, and I bring it up, and I plonk it in the middle there somewhere, doesn't really matter where, and I need to wire it up. So essentially I've got the same circuit as before, but now what I've got is a capacitor in place of the resistor. Now the impedance for a capacitor, I've said, is equal to 1/2 pi FC. Now what that tells me is it tells me that the resistance goes down as frequency goes up. Let you absorb that for a second. So with a capacitor, if I increase frequency, its impedance or its AC resistance goes down. So what I want to do here now is a series of very simple experiments. So if I put in here, now I'm going to change the frequency here to maybe 100 hertz or something like that. Something quite low. It's not critical what it is as long as it's relatively low. So if I put 100 hertz in there and I press the run button, I get the same straight line as the young lady did earlier. But if that's really what the problem was, I think, Mike. In that case, it was the time base that we're seeing there because of the very low frequency. So if I put 100 hertz in there, you'll notice that we've got scale 5 volts per division. So that's, and it's RMS, of course. So actually, I'm getting out pretty much what I put in there. Let's just wire up like we did before, the inputs and the outputs, so that we can see those together. So all I'm doing is I'm using the oscilloscope to measure the input and the output simultaneously. Actually, it did work live, which I didn't think it would. Now you can see those two waveforms, and you can see that the input, which is the slightly taller one, is pretty much the same as the output. There's a phase shift there, which is interesting, which we can talk about. But you'll see that the amplitude is roughly the same as at the input and the output. But watch what happens when I increase the frequency of this. We need to stop the simulation. If I increase the frequency of this and I make this, let's just make it 10K, so 10,000 hertz, 10 kilohertz, and I OK it. Watch what happens now. Nothing at all. I've killed my waveform. So, in the spirit of what we did before, I'm just going to unwind what I've done. Let's run it again. Let's have my waveform, Mike. Where's my waveform gone?
Where's your waveform gone? What have you got here? You've got a 10 volt, 10 kilohertz, 1K, and you've got a bit of a RC circuit going on there, have you?
I have, yep. And what I would expect the amplitude to drop.
Yeah, and so and you've got both of those. So I think you need to stick in your B channel onto the V1 to get a reference wave up first. So
Yeah, I did, and I got nothing for both of them. So I think, as in that previous example, the oscilloscope has got itself in a twist.
Yeah.
I'm just going to put another oscilloscope in. That's really annoying, that does it. So we've had 2 cases of that this morning, so there's obviously a bug in there. So that's, I think what it was is I made an adjustment while the simulation was running. I don't think that's a terribly good thing to do. Okay, now let's run it again. So you might say, well, I've just got a straight line coming out there. Well, I haven't actually, because if you notice, if I change the scale here to be quite small, you'll notice I do have a waveform here. I've got to change the time base, of course. You'll notice I do have a waveform here, but it's 200 millivolts per division, 0.2 of a volt. Well, before it was 10 volts. So 0.2 of a volt, and all I've done is I've changed the frequency. So at 10 kilohertz, I get 0.2 of a volt peak to peak here. If I stop the simulation so I don't corrupt the oscilloscope, and if I change this back to something a bit more reasonable, well, not that 10's unreasonable, but something to 1 kilohertz, for example, and OK it. So with 10 kilohertz, we were measuring 0.2 of a volt, peak to peak, from here to here. Now look what happens if we run this with 1 kilohertz. My word. So it's suddenly much bigger. So I've got to change the scale to even be able to see it. So now it's 4 volts peak to peak, 2 volts per division, 4 volts peak to peak. But all I did was change the frequency. I'll let that sink in for a second. So I've got a circuit here that the output, or the amplitude of the output, is proportional to the frequency that I feed in. Put another way, if I increase the frequency, I get a lower output voltage. If I decrease the frequency, I get a larger output voltage. That's actually quite obvious if you think about it, because as the frequency increases, the capacitor conducts better. So at high frequency, this point here is just conducted straight down to ground. So in other words, at very high frequency, and let's do ridiculously high compared to the experiment we're doing here, let's do 1 meg. I would expect pretty much a straight line to come out there. I will still be able to measure it, and I'll just show you when I do the measurement. So we run that, and you'll see there's a line coming across there. That looks like DC 0 volts, doesn't it? Let's just speed that up a bit. So we've got some chance of seeing it. Now I'm going to play with the volts per division, and hopefully we're going to start to see a waveform, but it's going to be pretty small. Change the time. Starting to see the waveform there, look. Now each one of these divisions here is 1/1000th of a second. Well, that makes sense because we're putting a waveform in of 1 million hertz. But look at the scale, 2 millivolts, 2 1,000ths of a volt per vertical box on the scale there. So I put in a very high frequency, I get hardly anything coming out because this capacitor has gone into full conduction. Whereas if I stop the sim and I go back down to something relatively low, let's go down to 500 hertz, for example, and run the simulation again. It's so big it's off the scale, so I've got to change the values here so that we can see it. 200 millivolts, 500 millivolts, got to change this scale as well for the time so that we can actually see the waveform. Up it comes. I see there's something in the chat, Mike. Can you just have a quick look at that? Yeah. And look at that. So that's 5 volts per division. That's 10 volts peak to peak. So I've gone from a couple of millivolts to 10 volts output, but all I did was change the frequency. So I've got a frequency dependent circuit. And what's a frequency dependent circuit called, Mike?
Sorry?
What's a frequency dependent circuit called?
Resonator, oscillator?
Filter.
A filter.
A filter. So it filters for me. This particular circuit lets low frequency through and it blocks high frequency. Isn't that clever? So all I'm using is a resistor and a capacitor, and I can throw away high frequency and I can keep the low frequency. A low pass filter. Where would I want one of those? Lots of places really, but imagine a telephone conversation and you've got high frequency hiss and noises in a telephone conversation, but the majority of the human voice is just below 10 kilohertz. So I would want this kind of circuit to throw away the noise when I speak into
you sharing the screen? Yeah, you're sharing the screen. Good. Just checking, that's all. You know, it disappears.
Yep. Oh, sorry. No, what happens when I sit back a little bit? It's I just disappear because of the screen background. Okay, I'm going to stop that simulation. I think actually we're well overdue for a comfort break. I'm going to stop the share. So what came in on that, Mike?
Oh, that was a slightly unrelated question, but a very challenging one anyway.
Okay, nothing's coming on the chat. So you've got a very complicated one. Did you manage to answer it?
Oh, I think so. I mean, it was an interesting one. Certainly, it's an interesting of when you can, Ohm's law and power and everything. It's all very simple, isn't it?
Mm,
And so, if you can calculate that you have so many watts on one end, and you want to send all those watts to another end, then really the only losses you're going to get are the resistance in the conductor, isn't it?
yep, absolutely.
But then if you put that into an RF world, ooh,
Yep.
a whole crate of new complications introduced.
Oh, yes, indeed.
Like propagation resistances and effective gains and all sorts of things like that, impedance matches and they all sap away your current. So I think it's yeah.
Okay, guys, we're gonna just have a quick comfort break. I'm gonna put the kettle on. I would suggest about 10 or 12 minutes, something like that, and then we'll rejoin. Make sure you can do that simulation that I just did with the AC waveform and change the input frequency. Now, don't make the same mistake I did of changing it while the simulation is running, because clearly Multisim doesn't like it. And I think we found a bug in version 14 that if you do change it while it's running, it's going to sort of crash the oscilloscope or the measuring device. And we've now seen that in 3 cases, myself included. So we just need to be a little bit wary of that, okay? So 56, let's rejoin at 11:10 once we've all had a chance to stand up and walk about for a few seconds. Okay? See you in a minute, mate. And welcome back. I was going to say to the second half, but it's a bit of a biased second half. This one we've only really got about 40-45 minutes left of this one, but we're well on target to do what I intended we would be doing today. So I left it recording just so that there's one Zoom link rather than lots of Zoom links, and I'll put that on the page when we do it. So can I share my screen? Possibly. What time was that? 11:11. So let's have a look at that one, Mike.
We've got someone raising their hand at the moment.
Okay. Who's that? Who's raising their hand? Hello, go ahead.
Hello, can you hear me, sir?
Yes, very well.
Yes, sir. I have a one question. I want to share my screen.
Okay.
Yeah.
Okay.
Yes, just 1 minute.
Should be able to share now.
Yes, sir. This one. I want to change this one, sir. But this one is not removed. This area.
Well, you mean you want to change the value of that variable resistor that you've put
Yeah, sir.
on there?
You're on the wrong tab.
Sorry, sir.
You're on the wrong tab. You've gone through the long part of the variable resistor rather than the.
Yeah, sir. I want to connect this one, but he's cannot connect this area. This one, this area.
No, your wire needs to go to the middle pin of that variable resistor, not the 2N pin.
Okay.
Yeah, and then you will start seeing a change when you change the value of your variable resistor. So it's actually your wire that's in the wrong place. If you
Yeah,
go
this.
no,
This
no,
one,
no, 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 no. On your circuit, go to R2.
yeah, this one.
Yes, that bottom, any one of the wires, the bottom one or the top one, move one of them to the arrow in the middle.
Okay, sir. Okay.
In other words, move the ground to the arrow, or well, that's one way of doing it.
Okay, sir. Thank you for confirmation.
Yeah, and also on the other side there, for some reason or another, you seem to have joined the negative side of the oscilloscope to the positive side of channel B. So I don't know why you've done that either, really.
Yeah, that will short the scope out and stop
Yeah.
the scope working properly.
Okay, sir. Thank you.
Okay, no problem, no problem.
Okay, sir. Can I stop this screen?
Yeah, stop your share. Yep, please.
Yeah, thank you. Well, sir.
Maybe I
Okay, it's a shame you can't do that with a single button press. There's 2 button presses associated with that sharing.
yeah.
Okay.
Let me just quickly make sure that he's actually. What I just want to do is quickly just.
Yeah, go on, Mike. Just
And
it's a
if
job.
I
You
would-
haven't got a visualizer there, but just show it on the screen on a piece of paper. I can see what he's trying to do. He's a little bit ahead of what we
a little bit ahead, isn't he? But it's good. It's good. It's good. Let's just say we have a battery, and that goes to ground, and then the other side
Right,
of that.
we know you can't see what Mike's doing, but
I'll show you in a sec.
he'll show you in a second. He hasn't got a visualizer.
So there, and then it goes here. Now, as you can see, that and then we have the measurement point here. Okay, so that was the circuit that was basically just shown.
Mm.
The 2 resistors. Now, what the gentleman had done there is he had turned one of these resistors down here into a variable resistor, like so. So theoretically, you could spin it and adjust the voltage. But if you wanted to do that, you would have to modify the circuit so that you take a wire, so that you disconnect the bottom. You take that wire off there, and then the second part of that resistor goes to the middle point of the resistor. Yeah, that's how that circuit would work. So it was actually a wire connection problem that was going on. This bottom of this resistor doesn't need a connection at that point, does it? It just needs to go from the middle point of the resistor, because the actual resistance on a variable resistor is the resistance between the position of this and the position of the other connected part of that resistor.
Either end of that connected part. Either end. Yeah.
Hopefully that cleared it up. I'm not sure what we were trying to say got through.
Yeah.
It's hard to know over Zoom, isn't it?
Yeah. We got another one coming on Q&As. It says, okay, so I got it then. Actually, decreasing the loss from the signal is really about the frequency too. I'm not sure about the explanation there, but the takeaway from that is that, yes, the loss, if you like, yes, that energy is being dissipated somewhere. But yes, indeed, the signal making its way through to our output terminal, which is where the oscilloscope is changing as a function of frequency. Yeah. So
and it's fair to say as well that the low frequency you got doing larger propagation distances anyway, don't they? You're gonna
yes, that's right. So let's go back to share screen. I press the share screen button, Mike. Oh, I've been disconnected. I've been disconnected. That means I've lost my drawing. How frustrating. Okay. No, it doesn't. No, it doesn't. I think it remembers. Come on, come on, come on. You can do it. Hey, I thought it was going to rob me of my drawing, but it didn't rob me of my drawing. Right, something big that I need to tell you is that when you save something and you save it to the local drive, that's the local virtual drive, and you'll lose it. So save it to your M drive, or save it to, there's other drives that you have provided by the university, isn't there? But don't save it to your C drive or you will lose it, okay? So your OneDrive, that's the thing my brain was wrestling for. So save it to either M or OneDrive, and that's your local drive that you'll keep. Okay, so we saw the magic. We saw the magic here. We've got a capacitor which changes its impedance according to the frequency that it sees. And what we can do is we can change the frequency here and we can measure the amplitude. Okay, I think most people can do that. So we could plot a graph. We could see what the output amplitude is as a function of frequency. So in other words, we could plot a graph with frequency along the x-axis and amplitude along the y-axis. What would that graph look like? Well, it would have a high amplitude at low frequency and a low amplitude at high frequency for this particular circuit, because this particular circuit is a low pass filter. Again, if you want to know more than the theory of it, I've done it for you here. Intro to AC analysis, capacitors and Laplace, inductors and Laplace, low pass RC filter analysis. These are all videos here, about 5 to 10 minutes long, that you can watch explaining all the theory on those, okay? I think we've got Q&A coming, Mike. Okay, something good I'd like to be able to do is I want Multisim to plot this graph for me automatically. How can I do that? Well, I can do that, actually. I can do that. I just got to remember how to do it. No, I can do that. So what I can do on this particular circuit, and I'm getting a bit of lag on there. Are we okay on the Q&As, Mike? We don't need to stop for anything on there? I'll take the silence to mean yes.
Yes, it's all good. It's all
okay.
Good.
So on this one here, what I can do is I can actually run a kind of a simulation here, and I can plot that graph almost automatically. But before I do, I need to put a connector on there, and Remember which connector it is, Mike?
It's what were you trying to do?
I'm trying to do an AC analysis, so it's the hierarchical one, isn't it?
Yeah, it's the it doesn't matter, I don't think, but yeah, the hierarchical one should do it. I
Well,
mean,
we'll go hierarchical. I
yeah.
think. Yeah. So you saw where I got that from. Place, because I'm going to get another one of them anyway. Don't go to component. Go to connectors, which is slightly down from there, and I'm selecting the hierarchical connector. Mike doesn't think it makes much difference. I don't think it makes much difference because this is about when we do the PCB design, this other part. So I'm going to put down another hierarchical connector and I'm going to put it there. Okay, I don't like the fact that they're horizontal like that, so I'm going to click on them and rotate 90 degrees like we're used to doing. Rotate 90 degrees. Now I actually want these to be able to probe my circuit, so I'm going to click away and I'm going to connect those up. So I want my IO1 to be on the input and my IO2 to be on the output. Okay, so all I really did there is I deleted the oscilloscope. Why? This connector is not connected to another page. What does that mean? Nothing. I just want to move that down slightly. Okay, that'll do. So I've got IO1 and IO2. It's sort of the wrong way around. That should be IO1 and that should be IO2. Doesn't really matter, does it? Now, my dream is that I could step through all of the frequencies and plot a graph, which I could do with a pen and paper, of course. It might take me 5–10 minutes to do it, and I wouldn't have that many points on the graph, but I'd certainly have some understanding of how the circuit was behaving. But Multisim's a bit cleverer than it lets on. So if we go into Simulate and we click on Analyses and Simulation, we get a new window come up. And this is the Analysis and Simulation window. Now, we're using an AC signal, and actually what we want to do here is we want to do an AC sweep, because that's what I just described to you, where you change the input frequency and you have a look at the output frequency. That's what an AC, so we want to sweep across all the AC frequencies. So we want Multisim to start at 1 Hertz, then do 2, 3, 4, 5, you know, so on and so forth, 1,000, 2,000, 4,000, 8,000, right the way up to some very large numbers. So we want it to sweep across AC so that we can have a look at the amplitude. That's what we want to do. So I'm going to click on AC sweep. And you'll see on the right-hand side, there's a whole series of different pieces of information. So start frequency. What frequency do I want it to start at? Well, 1 Hertz. 0 Hertz, remember, is DC, so we're not really interested in 0 Hertz. So 1 Hertz as a start frequency will do. Stop frequency, well, what should we say? We saw that 1 megahertz was pretty sort of close to 0, so let's go to 1 megahertz. Let's just see what happens if we do that. Sweep type, or we can do decade, octave, or linear. And the vertical scale we can plot as logarithmic, linear, decibel, and so on. So let's just go linear for the time being, and we'll see what happens when we change those parameters in a minute. Okay, Mike's head's in the way on my image. How am I going to get rid of Mike's head? That's I'll move him over there. Okay, so what we've got there is that's the frequency that we're going to scan across the across that circuit. We now need to look at the outputs. Well, at the moment, what outputs do we have? Well, I'd be interested in IO2, most definitely, because that's the output. Yeah. So I'm going to click on IO1 and I'm going to add onto this other side. Okay. So now what I've told the simulator is I'm interested in point IO1. Down the bottom here, we've got the run. It's very tempting not to press the run button, so let's press the run button and see what we get. Oh my word, look at that. Oh my word, look at that. Isn't that exactly what we were looking for? So what we've got the magnitude running here. That's the peak to peak. That's the size of the waveform, the size of the AC waveform. But as we go up in frequency, look, it's pretty constant. Follow my cursor. It's pretty constant. And then all of a sudden, as we get above about 100 hertz, we start to see it falling down here until the magnitude, notice the scale here. So this is actually 0 here. You notice that in excess of 1 kilohertz, it starts to get very, very close to 0 indeed. This one here is the phase, or the phase change, and you can see it stepping back to minus 90 degrees. In other words, when this gets to 0, there's been a 90 degrees phase shift. So we've got, as we increase the frequency, we see the amplitude decrease. That's absolute.
You've invented a base machine, John.
I've invented a phase machine, yes.
No, a base machine.
A base machine.
Yeah.
Yeah.
You've just kept all the bass and you've thrown away all the vocals.
Yeah. Well, I'd like to do that with most modern music, actually, Mike. It's, but that's ageism, isn't it?
Yeah.
Or inverse ageism, actually. Yeah. So let's do that again for those that were fumbling with it and ran into a few problems. So I'm going to close that. So you saw what I did. I placed a connector, and Mike says it doesn't matter. I don't think it matters, but I chose the hierarchical one, and I'm not going to, well, I will do it because I can delete it, can't I? So I take the hierarchical connector, put it onto my drawing, and obviously wire it up to the point I'm interested in. Now you notice I'm not doing IO2. I'm not looking at IO2 because that's the input. And I kind of know what that is. That's just going to be a straight line across all frequency. But you can plot that as well if you want. So I'll just get rid of that one. So I've got my probes, if you like. This is like having a piece of measuring equipment on there. This one here says 10 volts RMS 500 hertz. It's not. It's the one that's being stepped through, but you have to have the signal generator there, otherwise it won't be able to simulate. Don't ask me why Multisim wrote the simulator that way, they just did. And we just need to live with that. So you need a signal source on there, but what it's going to do is it's going to get hold of these numbers and it's going to automatically step through for you. So I go to simulate, I go to analyses and simulation, I choose my scale on here, so feel free to change these parameters. I suggest 1 megahertz is sensible because I kind of understood when the circuit was going to go to 0. So that's why I chose 1 megahertz. Sweep type, I could do decade, octave, or linear. Look those up if you don't know what they are. And on this scale, which is the vertical scale, I can do logarithmic, decibel, and so on. And so on. But linear is the most meaningful for this, I think. I go to output, and on the output, well, let's just remove that for the time being. So on the output, which one do I want to look at? Well, I want to look at IO1. I add it, and then finally I run it, and it's my wonderful waveform. I've just got to save the postman again.
Hopefully everyone understands the relationship between this graph here and the actual input signal and the output signal that will be happening. So when we look up, if we look here, for example, this represents 10 hertz. So if we had a 10 hertz signal coming from this signal generator here, going into the circuit, we would be going in here, and we can see that the attenuation that that signal gets is practically not, it actually, flies through no problem. However, the faster the frequency of that input signal becomes, the more attenuation it gets. So at this point here, we're looking at a signal which is 1000 hertz, which is 1 kilohertz, and you know, in terms of sound, is a beep kind of sound. Down here, we've got the 100 hertz. So what's actually happening is this graph is showing that the sounds that are higher, those kind of sounds, are going through no problem, and the higher frequencies are being attenuated. And so this is an excellent example of a bass knob and an amplifier.
Indeed, yeah, it's a selective filter. And as soon as we start playing, as Mike says, with variable resistors or even variable capacitors, we have an immense amount of control over the signal which passes through. This is grown-up electronics. This is proper electronics. So, just going to unshare and just make sure we get everyone up to speed on that, Mike. Probably the crowning glory is I'm going to swap the capacitor and resistor once we get everyone up to speed and show that. So let's be clear about what this circuit is. This is a low pass filter. It passes low frequency and it blocks high frequency. The giveaway's in the name, low pass filter, okay? So save that Multisim design as low pass filter, okay? I'm just going to stop the share and let's have a look at the incoming. That was an old one, so there's nothing new on the chat. Q&As, Mike?
No, nothing new. We are still live, aren't we? It's not just
Yeah,
us.
they are. No. Well, we've definitely got the attendees there, and yeah. Well, I would take that in a very positive way because that means that they're following the steps, or I hope they're following the steps. Just going to sit on this for 2 minutes, Mike, just to make sure.
It's interesting though, because the practical terms of what you've just designed there. I mean, if somebody comes to me and said, "Oh, you know, we want a bass knob on this amplifier," then that's exactly what I would do. You know, I would get it up in. I would probably first of all, if in a real world scenario, I would probably first of all say, "Okay, you want a bass knob? I would get one of those large equalizers, you know." With all those slidey things, and I'd fill it on an input and I'd fiddle around until my client was happy with, yeah, that's the kind of bass change that I'm looking for.
Yep.
And then what I would do is I would look at the frequencies on that equalizer, then I'll plug those values into a simulator and I would build that kind of RC circuit there. And I would simulate those values to give me the same kind of curve that the customer then was interested in. And then once I have those values, I'll build a prototype and I'll actually physically test it, go back to the customer or measure it, compare it to my input values, tweak it, and go through that iterative process. So, you know, it's what that little circuit that you've shown there and the graph that you produced from it in the time you've done there, in essence, is extremely powerful because it can completely answer 1,000 questions for you just by a few clicks.
Yeah. The other marvelous thing about that circuit, Mike, is it's an introduction. So if the panelists, the attendees, rather, would like to have a look on the resources page, they'll see that I've put some videos on there about Laplace. Now, Laplace was a brilliant mathematician, and what he did is he described mathematically what's happening inside those circuits. Now, that's not a trivial thing to do because we're talking about differentiation and integration. In other words, inductors and capacitors require calculus to solve what they're doing. And calculus is messy. I equals C dV by dt. You imagine you suddenly put that into an equation and you say, what's it going to do at 10 kilohertz? That's a bit tricky. But under the Laplace, what he does is he does something marvelous, is he turns calculus into algebra. Now, hopefully, well, we're master's students, so hopefully you'll be able to do algebra. You could be forgiven for not being experts at calculus. Algebra is pretty straightforward, and there's some nice demos on the resources page that you might like to look at, which explain how you go from calculus into
Sorry, John. Could you just show how to apply the I/O component again?
Yep, sure, no problem at all. So I've got to remember to hit the share screen. I've got a big note in front of me, Mike, with share screen written on it.
Yeah, it's a tricky one.
Right, so let's just take it from the top. So I'm going to delete IO2 because I don't actually use it. I'm going to delete IO1 so that the participants can see it. Place, connector, hierarchical connector, bring it into the drawing area. Excuse me. Click on it. Not that, the whole thing. Rotate it just to make it look neat. And now wire it up. That's it. So that's the connector connected to the circuit. Now I go to simulate, analyses and simulation. I need to set up my parameters here. So start frequency 1 Hertz, stop frequency 1 megahertz. I invite you to play with these. I'm on decade and I'm on linear. Feel free to play with the other parameters as well and you'll see what happens. On the output, which is the thing I think that you're talking about, so I'm going to remove that for the time. How do I add IO1? I click on it on the left-hand side. I press add, and it's over here on the other side. So that means it's going to be a variable which is analyzed. I press the run button, and there's my wonderful graph. Also, this graphical viewer is really good. There's all manner of things that you can play with up the top here, where you can put cursors on, you can put grids over the top and everything. Play with those, you can't do any harm there. So have a good fiddle around with all the parameters which are on there. You'll notice that it records the previous ones for you. So all of the ones that I've done previously, which is quite a lot, more than I realized I had actually, are all recorded previously in this graph. Okay, what else has come in, Mike?
We just have a question of, is Multisim available for download?
Student version is, yes, it is.
Yeah, it's got a reduced component count, isn't it? I think
it has reduced component count, but for this kind of work that we're doing here, it would be more than adequate.
And there was the last one. I mean, you've just hopefully answered the question from the anonymous attendee of how to apply the IO component. Yep. And from Zerin, I'm going to have a guess that that's pronounced Zerin. He's not getting any output at the moment, so if he's still got a problem, which I think he has because he's raising his hand, maybe we can share his screen.
Yeah, okay, let's do that. So Zerin, remote to panelist, and now I need to go to panelists, and so, okay, Zerin, you're co-host. You can share screen now.
Give me if I pronounce your name wrong.
Yeah, tell us if we got it right or wrong. Hello? Hello?
Yeah, sir, can you hear me?
Yeah, fine, yeah.
Okay, sir, I want to share my screen and also wanted to share you the thing. The matter is I can do the simulation and analyze and simulation, but I didn't get the save and run button. I don't know why it's not showing here.
Okay, show us the circuit diagram first, please. I'd like to see the circuit diagram first. Share your screen first. Let's get that hurdle over. Okay, we've got your screen, or starting to get your screen. Yep, good.
Can you
I can, but shut that window down. I want to see your circuit diagram first, please. So analyses and simulation shut down. Yep, good. Just shut that. Yep. Let's see your circuit. So you've got IO1, IO2. That's perfectly fine. Nothing wrong with that at all. Okay.
Okay, yep, that's good.
Yep, it's good. Simulate. Analyses and simulation. AC sweep, that's correct. Up to 1 megahertz is fine. decade
Except the
logarithmic.
problem started here. I didn't see any save or
Yeah, your screen is too low. So your zoom level on your browser, this is what we were talking about before.
Yeah,
If
yeah.
you change the zoom level on your browser by pressing the control button and scrolling your mouse on your browser, you'll change the resolution of the Horizon virtual machine. Because at the moment, that window is too big for the screen resolution it's giving you. So all you need to do is zoom your browser in and out, and it will change that resolution.
So press the control key followed by the roller ball on the mouse.
Maybe you could give an example, John.
Yeah, well, they may not have a roller ball. That's one of the problems
It's
of doing
nothing.
it. Yeah.
It's nothing. The way that Horizon is deployed is that how it decides the resolution of its desktop is down to the resolution of your browser at that point. So if your browser can zoom in and zoom out, which most browsers can, you can change the size of that screen. And I think John might be able to show you now. If he loads up his Horizon and then he zooms in and out, it'll give you an example of replicating that problem that you just had.
Well, I'd like to, but it's just shut me out. I think you're setting me up to fail there, Mike, because I tried this morning and I couldn't do what you said.
Oh really? Oh, because Lewis was doing it quite live. It's your browser where you have to zoom, not inside the Horizon thing. That's the key here. So you might have to just make sure that your browser in a window that's not maximized on your desktop already. Yeah.
Yeah, no, I can do it, Mike. I can do it.
You can do it. Okay.
Yeah.
Oh,
So-
sorry, sir. My connection was dropped.
Yeah.
No problem. No problem. What we're going to do is we're going to share John's screen now, which will replicate the problem that you've got, and then how to fix it. Okay.
Okay, so what I do is I click into the window, I hold down the control key, and I move the roller ball backwards and forwards. So I'm going to click in somewhere in the window here.
You might have to click the tab on the top. Yeah, that's it. Oh no, that's just doing the window you're in.
That's
If
just doing the window I'm in.
you click your browser tab on the top, yeah, where it says VMware Horizon, yeah, click up there. Now press Control and scroll.
Yeah, I am. It doesn't do it.
I wonder if that's because you're using Chrome.
Might be because I'm using Chrome. I don't know.
I know in Firefox, if I'm in Firefox,
Yeah.
I don't know if I'm able to, can I share my screen?
The other way, Mike, the quick way, is just to change that screen resolution that I did here. So we're looking for a quick fix on this, aren't we, at the moment, until we can play with it. So what I do here is display settings. Okay. And down here, it says change the size of the text, apps, and other items. You can adjust that size here. I'm on 250% at the moment. But if I go to say 100%, watch what happens. Look, can you see that? So there'll now be, well, I can't even use that. It's too.
Okay, you back with me? Okay, is that okay, Devin?
Hello. So I have to change my laptop's display settings.
Yeah,
You're saying that.
yeah. Just
Not your laptop. No, not your laptop. It's not your laptop. It's you either display the zoom value of your browser,
yeah.
or you change the display settings of the Horizon.
Oh, okay.
Yeah, that's one of two ways. I don't know. Am I able to share my screen?
Yeah, of course you are. You're co-host.
Who can share? Only hosts or panelists? No, only hosts. Fine. Right. Okay. Let's do this. So if I show you, so for example, if I'm looking at okay, can you all see my Firefox there?
Oh yes.
Yeah.
Okay. If I hold down Control and move my scroll now, you see I just zooming in and out on the browser, and that actually has the effect of changing the resolution in Horizons.
Oh, okay, I got it now.
Yeah. Just
Okay.
let us know if that's fixed it for you.
Yep, let us know how you get on with that, please.
Yeah, sir, the problem is solved now. Thank you so much.
Fantastic,
I got it.
fantastic. Thanks. Right, withdraw.
So that also hopefully RX20884. When we looked after him earlier, were you was he the person we were trying to find earlier when we were?
I think he was, Mike. I think he was. Well, we'll take any incoming that he has from us. Can I just do something else for the others, and we can deal with the fallout in the next little bit? I just wanted to get to the point where I swapped the resistor and capacitor over. It's pretty much the same exercise, so if people have done that okay, they shouldn't have any problem with the next bit. So I'll just do that, and then we can draw to a close for most people, and we'll take anyone that's got any problems after that. Right, so we've got this circuit here. Now what I could do is I could delete these two components and swap them over, but if I delete them, the circuit will fall apart.
Share
So
your
what I
screen.
can... Script, thank you, Mike. It's so easy done. You're flicking from one to the other and back again and letting people in, letting people out. It's really, really hard. I've got the circuit here. What I'd like to do is turn R1 into a capacitor and turn C1 into a resistor. If I delete this, I'll lose all my connections, which I don't want to do. So what I can do is I can right click on it and I can do replace components. So I click on replace components, and instead of having to do a place, it just suddenly comes up as this. So I can just plug it in. So I want to replace R1 with a capacitor. Click on capacitor, 1 microfarad, that will do me nicely. Okay, and you notice that's become a capacitor. It's called C2, it doesn't matter. Right click on this one, replace components, and I'm going to replace that one with a resistor. Okay, Mike, if I run a simulation on that, what do you think the output waveform's going to look like based on your 30 odd years of expertise in electronic design?
I reckon that you may introduce the treble version of your bass control.
Treble version of the bass control that we had before. In other words, it's going to block low frequency and let high frequency through. That's pretty obvious actually, because the capacitor will conduct when the frequency is high, and when the frequency is low, it's just short circuit because there's a big gap in the middle here, right? Let's do it. Let's run it. Analyses and simulation. Same as before, 1 Hertz, 1 megahertz, decade, 10, linear, all the rest of it. Output, I'm just going to remove that for people that are uncomfortable with that. So I want to connect the output pin, IO1, that's the one I want to look at. Select variables for analysis, yeah. And then finally press the run button and yoo-hoo, look at that. So the magnitude at low frequency, if we look down here, 1, 10 Hertz, 100 Hertz, 1000 Hertz. As the frequency increases, the output amplitude increases. As the frequency decreases, the output amplitude decreases. I've just built, just by swapping those two components over there, a high pass filter, whereas before I had a low pass filter. So now what that means is for any input waveform, I can control the low frequency component, the high frequency component, even the mid-range if I want to a certain extent, by carefully selecting the component values. So if I start playing with the value of the capacitors, the values of the resistors, I can change the shape of this curve. In other words, where it goes from low to high. In other words, where the cutoff is. That's what the word is used, cutoff. It's where the filter changes. Okay? So we're at that point, Mike. So I think the people that haven't had any problems with that so far, Feel free to experiment. I invite you to change the values of the resistors, capacitors, and so on and so forth. Okay. But what I think we ought to do is just clear up. So if you're happy, everything's worked okay. Oh no, that's from, I'm reading something from ages ago. If your circuit's all worked okay, you're happy with it, you've got your high pass filter working, you've got your low pass filter working, that was really the learning outcomes for today. That's a major, major step forward, that we can do an AC analysis, you understand how a scope works, you've injected an AC waveform, you can see the waveform coming out, you're getting comfortable with the simulator. This is all good, 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 solid achievement. Where do we go after this? Well, next week we start introducing the PCB to you, because we have to, because you need the PCB design for your assignment, okay? But we've sort of pulled you through some of the key elements which go into making up Multisim and making up Multisim simulations. So hopefully now you can see there isn't a bunch of difference between doing this in simulation and doing it for real life, because we can do pretty much the same thing. Okay, so if you're happy, go and get yourself some lunch. If you're still stuck on a particular thing, hang into the webinar and we'll have a look at you in a second, okay? So if you're happy, see you later. Maybe you'll come along to the, well, it's not like a soap opera, EastEnders or something. It's not an exact repeat. It'll be a similar repeat this afternoon.
We might throw in some new jokes.
Well, yeah, assuming we find some by then. We've been using the same ones for the last 10 years. Tried and tested though, Mike, tried and tested.
Yeah.
Okay, so feel free to drop out now if you're happy with things. And if you want a little bit of assistance outside the time, then hang on in there and we'll do what we can for you. Okay, see you later.
It's funny how you feel you have to give that pause as well, isn't it? So RX20884, do you still have a problem? And are you still here? If you so, we can share your screen and try and fix it for you. We have Abhavna Bari has raised a hand, John.
I think let's have a look. People going out fairly rapidly now. I can't see the raised hand. Where's the raised hand?
There was a raised hand request from Bar.
I've got no raised hands on the attendees now. Must have lowered their hand, Mike.
Okay. Let me just.
Well, if you can see them, if you can see them, you get on them. Nothing new in the Q&As. It's quite handy having these two ways in, isn't it? Because the Q&A is sort of, I suppose the Q&A is supposed to be for everyone, but it actually works the other way around. People are using the Q&A for very personal, individual questions, and they're using the chat for the more generic ones, aren't they? It doesn't matter which way around it is, but
as always with our electronics modules, we're happy to help with any electronic things, aren't we? Whether it's what we're doing, or chat about it, or answer any questions or queries as best we can. It's always interesting, isn't it?
Okay, Harry, so we've still got a lot of attendees in. That either means that they've fallen asleep, died, or...
My laptop mouse does not have scroll. Is there a way I can do it? Yes, there is. TA20116. There is. You can use the browser zoom function. So you can go to your browser and go to the settings in your browser, and there'll be a way to zoom in and zoom out the page you're looking at. Yeah.
Do you want to share screen and show that, Mike? Might be easier.
Yeah, I will do that. Let's try that. So if I gave an example, if I load my browser up again, yeah, okay, and we'll share that. Here we go. So here I have my browser. So me holding down control and scroll wheel is doing exactly the same as me going to the settings and finding my zoom option and doing it that way. And each one of those zoom incrementations will have a change of the resolution of the Horizon virtual desktop.
Yep, brilliant. Thank you, Mike.
Excellent. He's got it.
Okay, well, I think a lot of people here have probably gone off for lunch, but without closing their browser. I'm just going to stop the recording because I think